Hello everybody and welcome to our next video on asymptotes. And so we just finished talking about the fact that an asymptote is like an imaginary line that cannot be crossed. That is true for vertical asymptotes, but not necessarily true for horizontal or oblique asymptotes. Here's an example of how we would calculate some of those. So if we have this function here, then we've already expressed this function in factored form. That's our first step. And we find the zeros. So the zeros of the denominator are -2 and +3. If x equals either of those values, then the denominator will equal 0. So we have vertical asymptotes where x equals -2 and where x equals 3, because if we were to divide by 0, that would be a problem. It's undefined. Okay. Now, also, if we were to plug this number in for x in the numerator, we would see that we'd get a number divided by 0. So whenever you have a situation where subbing this in would give you a number over 0, that means you have a vertical asymptote. If you got a situation where the numerator and the denominator are both 0, 0 divided by 0, that's when you have a hole in your graph. Okay. Now, also we notice in this function that the degree of the numerator is 1 and the degree of the denominator is 2. So since the denominator has a greater degree than the numerator, it grows much faster than the numerator does, and therefore there's also a horizontal asymptote at y equals 0. If we want to find oblique asymptotes, we need to find the quotient of the numerator and the denominator. We do that by doing polynomial division, like we learned earlier in this course. If there are any remainders, we can disregard them because we only need the quotient. The graph of a function can have either a horizontal asymptote or an oblique asymptote, but not one of each. And that's because of the rules that relate to oblique asymptotes. So for example, if we have this function here, we know it will have an oblique asymptote because it has a degree in the numerator that is 1 greater than the degree of the denominator. So I find the quotient by dividing x minus 1 into x squared plus 8x minus 20. Doing some long division, I see that x goes into x squared x times x is x squared, and x times -1 is -x. There's a little typo in my original note. When I subtract those, I end up with 9x. Okay, 8 minus -1 gives me 9x. X goes into 9x 9 times, so 9 times x is 9x. 9 times -1 is -9, and when I subtract, I get a remainder of -11. What really matters is the quotient, okay? The quotient is the equation of the oblique asymptote. So this function approaches the slant asymptote at the equation y equals x plus 9. Okay, the remainder doesn't really matter because as x gets really, really big, this expression gets closer and closer to x plus 9. Finally, if we're finding the horizontal asymptote for a rational function, in this case, the degree of the numerator and the degree of the denominator are the same. So we know that we're going to have a expression for y. We're going to have a constant, not y equals 0 for our horizontal asymptote. Okay, and the reason again is because we're finding the limit. Sorry, I don't know why this doesn't want to work here. There we go. We're finding the limit as x approaches infinity of this function, 2x squared minus 4x plus 8 all over 3x squared minus 27. To do that, we're going to factor out the greatest power of x. So the greatest power of x is x squared. I'm going to factor that out of the numerator. That's going to give me 2 minus 4 over x plus 8 over x squared. And it's going to give me x squared, sorry, that's a squared. It's going to factor out the 3, and I'm going to have 27 over x squared. And this seems weird, but the idea is that as x approaches infinity, this is going to be like 0, this is going to be like 0, and this is going to be like 0. So I'm going to end up with, and these x squareds are going to cancel out, so I'm going to end up with just 2 over 3. We're going to look at some more examples in our next video.